finally going to get started with the C programming language. This is a lecture that's a companion for the book, Introduction to Real-Time Computing for Mechanical Engineers, a lab-based approach. Check it out on the website. All right, so a little longer lecture today. Let's get into it. Getting started with C. In this section, we will introduce the basic elements of programming in C. We will use C to write code for the T1 target system in the lab exercises, okay? So there's one for each chapter of the lab exercise. We're going to be writing those in C. We encourage the reader to supplement our book with the books listed here. The Kernighan and Ritchie book is the classic, highly recommend as your first introduction to C. Working through the tutorial introduction would be a really good way to get started on the right foot. Obviously, we'll do our best to teach you C in this course as well. But this isn't a course on C, it's a course on real-time computing. So yeah, those other resources are going to be a little bit more focused on the C programming language, and highly recommend getting familiar with those. All right. First off, a sandbox for C. Before proceeding, make sure that you've done the sandbox for C section and you've set up your own sandbox in Eclipse so that you are able to follow along with the examples that we do in this lecture. Okay, elements of a program: functions, data types, declarations, libraries, the basic elements. So, data types, declarations, and assignments. In C, to declare a variable, you must specify its data type and name. Here's some common data types. Char, for character, represents a single character. For example, the character A. Int represents an integer. For example, 5 is an int or integer. Short is a small integer using less memory. As we'll see, each of these objects is going to take a certain amount of memory, and a short integer takes up a certain amount of memory. A long integer takes up a bigger amount of memory, but can represent more values, potentially represent more values, larger values. Float, a floating point number for representing decimals. For example, 3.14 is a floating point number. Double, a double precision floating point number for higher precision. For example, 3.14159, the first 6 digits of pi. This would be a higher precision floating point number than 3.14, but in many cases, instead of the floating point being, say, 8 digits long, the double is 16, for instance. Char, and then the brackets, a string of characters. To assign a value to a variable, use the equal sign operator. Often, we declare and assign a value in the same line as in the following examples. So let's assign and declare C to be a character and assign the value of A to it. This, by the way, is a comment here. So we see the syntax for a comment, the double slash. Int x declares x to be an integer. We also assign, initialize a value of 42 to that int. Float pi equals 3.14. We have a floating point number here. Double E, we've got a double precision floating point number. In these examples, these names were given to variables that have these values assigned to them. Literals, variables, statements, expressions, and operators. A literal is a fixed value in code, like 42 or the character A. These are literal fixed values in code. We'll enter them in directly. A variable is a named storage location that holds a value. Okay, we assigned variables like X and C on the previous slide. A statement is a complete instruction that performs an action. In C, statements end with a semicolon. And if you don't remember the semicolon, your compiler will remind you. For instance, X equals 42, semicolon is a statement that assigns 42 to the variable X. An expression is a combination of literals, variables, operators, and function calls that evaluates to a value. For example, X plus 1 is an expression that adds 1 to the value of X. So X plus 1 is an expression. Multiple expressions, sometimes just a single expression, will be in a statement before the semicolon. Okay, finally, an operator is a symbol that performs an operation on one or more expression called operands. For example, plus is an operator that adds two operands, as in X plus 1. So here X and 1 are the operands, and plus is the operator. Okay. Some terminology here that help us out. Functions. A function is a block of code that typically receives some input arguments, has one or more statements, and returns some value. Every C program must have a function named main. Okay, maybe a little different than other programming languages you've encountered. When a program runs, it starts at the first statement of main and proceeds downward. Any number of additional functions can also be defined, either in the same file or elsewhere. And if they are to be executed, these must all connect somehow to main. Otherwise, they'll never get executed. Consider the function int cube int x, talk more about that construction, braces, return x times x times x. There's no power operator in C. To do power, you have to use a function. But for now, instead of raising x to the third power, we'll just multiply x and x and x, which gives us x cubed. The function cube takes an integer x as input and returns the cube of x. The int before the function name, this one right here, specifies the return type of the function. So the type that the function is going to return. In this case, the function returns an integer. The int before the argument name x, so this int, specifies the type of the argument. So x here is the argument. The function is enclosed in curly braces. So we have the curly braces here. The return statement exits the function and returns a value to the calling statement. So the caller is somewhere else, somewhere that calls the cube function, maybe called cube of 93, for instance. That would be the calling statement. And the return statement returns whatever value the function evaluates to at the end to the calling program. Okay. Function prototypes. A function prototype is a declaration of a function that tells the compiler about the function's name, return type, and parameters. A function prototype is typically placed at the beginning of a file or in a header file, which is a separate type of source file with the extension .h. The function prototype for cube is given here, int cube int x, then we end it with a semicolon. Note that the difference between a function prototype and a function definition is that the prototype does not contain the function body. So when we define the function, instead of having a semicolon here, we had an open brace, right? And we actually filled in the contents of the function. For the prototype, you just have that first statement, and then you end it with the semicolon. Okay. Comments. A comment is a note in the code that is ignored by the compiler. We have already seen single-line comments which start with the // and continue to the end of the line. Multi-line comments start with / asterisk and end with */. For example, this is a multi-line comment. It can span multiple lines. This is often the alignment that people choose to use, although that's not strictly required. Comments are useful for explaining code, making notes, and temporarily disabling certain blocks of code or lines of code. Libraries. A library is a collection of functions and declarations that can be included in a program. The include directive is used to include a library in a program. For example, include stdio.h includes the standard input-output library, which is included in 99% of C programs. It's a very, very common standard library to bring in. The stdio.h library provides functions like printf for printing to a console and scanf for input. The stdio.h library is a header file that contains function prototypes and declarations. The actual library is linked during compilation. So the header file gives all the information that the compiler needs to know in order to set it up to link the library to your program. The stdio.h header file is included in the C standard library, which is part of the C language specification. Other header files from the C standard library include stdlib.h for memory allocation and math.h for mathematical functions. We use these a lot. Okay, preprocessor directives and macros. So the include directive, which we've seen a few times already, the include directive is a preprocessor directive that tells the compiler to include a library in the program. Preprocessor directives are messages to a preprocessor program that runs before the compiler. So remember, our source code goes to the compiler, but the preprocessor gets it first. The preprocessor handles these preprocessor directives before the compiler even sees your source code. Other than include, the most common preprocessor directive is define, which defines a macro, which is a symbolic name for a value or a code snippet. For instance, define max speed 100 defines a macro named max speed with a value of 100. We like to capitalize macros as a convention. Macros are replaced by their values, often numbers or other literals, before the program is compiled. So wherever you wrote max speed throughout your program, before the compiler even sees your source code, the preprocessor is going to replace that with literally 100 wherever it shows up. So it's almost like a variable, but it's a variable that the compiler never sees. We will later consider a more advanced type of macro called a function-like macro, which can take arguments and return values. Style. Programming style. Here are some general guidelines for writing C code and programs in a lot of different languages, but especially for C. Indentation. Use consistent indentation to make your code readable. Whereas in some languages like Python, the white space, the tabbing in, and indenting is part of the syntax. It is not in C. White space just gets gobbled up. But in order to make your code readable and maintainable, you should use consistent indentation. Comments. Use comments to explain your code, but be terse and to the point. Putting in a comment after x equals 3 that says x is equal to the value of 3 is not a useful comment. So we try to avoid those sorts of comments, but we try to leave behind as much information as we can to be useful to somebody trying to read our code later, which might even be us later on. Most often it is. Naming. Use meaningful names for variables and functions. For example, cube, which we used as the name of our function that we wrote earlier, is probably a better name than f. Okay, we could have just called it f, but it doesn't describe what the cube function does. Spacing. Use spaces to separate operators and operands for readability. So if you're going to write 5 plus 3, you should have a space in between there. That's a lot easier to read. Braces. Use braces to enclose blocks of code, even if they are only one line. Line length. Keep lines of code to a reasonable length, for example, 80 characters for readability. Consistency. Be consistent in your code style throughout your program. Okay, these are all helpful style considerations. Structuring a program, another element of style. Style guides often recommend structuring your program in a particular way. We use the style guide canon, which recommends the following order in a C program file. We start off 1, a prologue as block comments, describing the objects and operation of the file. So the prologue in a block comment. 2, header file includes with standard library headers before those that are user defined. Symbolic constant defines, then those that are function macros, so function like macros we'll discuss later. 4, custom data types are defined next, and type defs, then enumerated types such as enums, which we'll also look at later on. 5, global variable declarations. So again, we're going down our source file here. Local function prototypes that will not be exposed to other files first. If the function is to be exposed, its prototype should appear in a corresponding header file. Function definitions in some rational order, approximately descending in abstraction. So we have most abstract up top, and then we descend into less and less abstraction as we go down, more concrete as we go down. Yes, so that is the list. That's the ordering we should do in our program files. So we'll see a lot of examples, but that's the general guidance that we'll try to follow as much as we can. Okay, so here's a program for cube. Here's a complete program that uses the cube function we defined earlier following the style guide. So we have our prologue here. Okay, we have our includes. And these library includes, we have the standard input output library, which we're going to need for printf. We're also going to use the standard library header, just the std_lib, which provides the exit success constant, which we're going to use as a macro definition. And then next we're going to put in our function prototype. So we're going to define this function cube. We're not going to define it until the end here. So we start off with a function prototype. Technically you can put cube, the definition, up top, but we like to have main as our actual first function, and then the lower level functions below that. So the prototype should appear first, and then we get into the actual function definitions. So here we go. So we have our main definition here. So we're just going to define a variable x and initialize it to 3, and also declare another integer xc. Xc, we're going to assign the value that cube of x returns. So we're going to call cube of x in our main function. Remember, if we want cube to be called at all, it has to be called in the main function or by some other function that appears in main. And then we're going to use printf to print this statement to the console, print this string to the console. This is a formatted string, and we'll talk more about printf later, but printf allows us to print a formatted string. Inside the string, we have these special characters appearing. So %d says we're going to put an integer there. We have 2 of those showing up. Then we pass arguments x and xc to printf, and it's going to place the first integer that we pass in that location and the second integer that we pass in that location. So it's going to print this formatted string to the console. Then it's going to return exit success, which is whatever this macro evaluates to, which is 0. So exit success is what we are supposed to use as the constant when things have worked out correctly in our program. Often people will just return a literal 0 instead. Exit success does evaluate to 0. So people will often just put 0, return 0. If your main returns something other than 0, that is an indication that there was an error at some point. So the error code would be passed back. If the error code is 0, it's not an error at all. It means that you have successfully run your main program. Okay, then we have this another block comment that says raise an integer to the 3rd power, which describes what we're going to do in the cube function definition. So now that we are ready to define it, we start out again int cube int x. We open up a block, return x times x times x, and that is our cube function, just like we saw before. So this is a full program that if we run should print 3 cubed is 3 times 3 times 3 is 27. So let's go into Eclipse here. I'm just going to show you in my sandbox what happens when I already put the code in here. What happens when I compile this? So I can go to build, and I already built it, but if I clean the project and then I build the project, we'll see building target. This is the linker on my machine. In yours, it'll actually produce a .exe if it's a Windows machine that you're on. if you're in the development environment, it's going to be a Windows machine, and you're going to have an executable appear. So if you go to the debug folder, sandbox1 will appear there, and we can run this now. So we can run as a local C++ application, and we get 3 cubed is 27 appearing in the console. So that all works. Our first program is running. Okay. Oh, and then if you wanted to change it, so say you wanted to cube a different number, you could change this. Well, let's do 4. So let's rebuild this. Build project. And let's run as local C++ application. 4 cubed is 64. There we go. Okay, good. Moving on to algorithms, control flow, and arrays. Algorithms are sequences of instructions that perform some task. Okay, so this is a very broad definition of an algorithm, but it's often conceived of as a sequence of steps to solve some problem or to complete some task. There are usually many algorithms that can solve the same problem. So for any given problem, usually there are many algorithms that could be used to solve that problem. The choice of algorithm can affect the efficiency of the program. So the program, maybe there are a lot of ways you could do this task, but some are better than others, and some of them are going to be more efficient than others. We will discuss algorithms in more detail in chapter 2, but for now we will learn about some of the most important building blocks of algorithms: control flow statements. Okay, control flow statements determine which blocks of code are executed and in which order. So if you're going to implement any algorithm, you're going to have to be able to use these types of statements. The first one we're going to start off discussing is the if, else, else-if statements. So the if statement is used to execute a block of code if a condition is true. Okay, so we're using logic here, right? If this, then that. The else-if statement is used to execute a block of code if the if condition is false and another condition is true. The else-if statement is optional. You don't have to use it. The else statement is used to execute a block of code if the if condition is false and no else-if condition is true. The else statement is also optional. So here's an example of an if, else-if, else statement. So we have if a condition. So if condition is true, this block gets executed. So executes if condition 1 if condition 1 evaluates to true. If it evaluates to true, then it will execute block 1. And then it will skip the rest of this and move on to the line down here. Okay. Else if, so if condition 1 evaluates to false, then it will test condition 2. And if condition 2 is true, it will execute block 2. If condition 1 is false and condition 2 is true. Okay. if neither condition 1 nor condition 2, or if there are other else if conditions in here, if none of those conditions have been met and we have an else statement, this will be executed in the last ditch effort. Executes if no condition is true. Okay, so that's our most basic, most useful control flow statement, the if statement and its kin. Okay, switch statements. The switch statement is used to execute one block of code from among many alternatives. The switch statement is similar to a series of if-else-if statements, but it checks for the equality of an expression with a list of values instead of evaluating a condition. So, whereas in this case, we were evaluating to see if this condition was true or not, in the switch case, we're going to look to see if this expression is equal to case 1 or case 2 or other cases. Okay. In some cases, a switch statement can be more efficient than a series of if-else-if statements. There are going to be a lot of things like this, where we're going to say something like, in some cases, this can be more efficient than that. And the reason why it's wishy-washy is that compilers don't all do the same thing given the same code. So two different compilers of C might compile the code differently, the same exact source code differently. Also, there are different options you can use in the compilers where you can try to have the compiler make the code more efficient for you. And so it's difficult to make broad statements about efficiency. So we'll say things like in some cases. So using switch can occasionally make things faster, but sometimes the compiler will compile to the same exact machine code given source code that uses a switch statement or an if-else-if statement. So it's hard to predict. Here is an example of a switch statement. So switch, we have the expression, we have case 1. So the block 1 here is going to be executed if expression equals case 1. Case 2 is a different expression that is going to be compared to expression. And finally, we have default. So if none of these cases match expression, we'll execute the default. Default is optional. You don't have to use default. Now, you might notice that there's a break statement in here. And break will break out of this switch case statement. And the reason we have these in here is that it's very common that if you do have a match with case 1, for instance, that you don't want to then evaluate case 2. However, C by default operates as follows. It will, if it matches case 1, it will execute block 1, but then it'll continue to evaluate the cases that occur after. So it'll also evaluate to see if case 2 is true. Often we don't want that behavior. That behavior is called fall through. So we put a break statement at the end of each block to avoid fall through. Sometimes it is what you want. You want it to continue to test for cases. So in those cases, you don't need the break statements. Okay, so that's the switch statement. The next control flow structure is the for loop. A for loop is used to execute a block of code multiple times. The for loop has 3 statements. Initialization statement, which we'll call statement 1, executed once before the loop starts. So that statement gets executed only once, and it's before the loop starts. The second statement, statement 2, is called the condition statement, and it's evaluated before each iteration through the code block. If statement 2 is true, the loop continues. If statement 2 is false, the loop ends. Okay, so we're going to be evaluating this condition every time we go through the loop. And finally, update. The update statement 3 is executed after each iteration. Okay, so the way that the syntax looks for the for loop is for, and we have parentheses, statement 1, semicolon, statement 2, semicolon, statement 3, and then we have our block. So this block gets repeated however many times the condition allows it to be executed. So this executes statement 1. Okay, so it starts off with the initialization statement. Okay, then checks statement 2. If statement 2 is true, the block is executed, followed by statement 3. So the block is executed, and then statement 3 is executed. And then we go back to statement 2. If condition is met, if it's true, then we run the block again. Then we run statement 3. Statement 2, block again, statement 3. Statement 2, condition checking again, block, statement 3. So we just go here to the block to statement 3 to statement 2. Okay? That's the loop. So here's an example of a for loop. So we have the for, we have our initialization statement, int I equals 0. So we're going to start off some integer I at the value of 0. That's our statement 1. Our statement 2, which is the condition statement, is that I has to be less than 5 for us to run through the block. And finally, we have our update statements. 3, I++. I++ is shorthand for I equals I plus 1. So you now might have an idea of why C++ is a programming language that's built off of the C programming language. It's an iteration. So we take I, we add 1 to it as a very, very common shorthand for I equals I plus 1. Okay, so how many times is this block going to be executed? Let's think about it. It's going to initialize I equals 0. Then we're going to evaluate our condition statement, I less than 5. 0 is less than 5, so that's going to be true. So we're going to execute the block. So there's we'll do it for I equals 0. It will run through the block. Okay, great. Ran the block. Now we're back to the update statement, I++. We're going to add 1 to I. So I is now equal to 1. Well, I is now equal to 1. Now we need to see if it passes our condition. Still less than 5, so it will run the block for I equal to 1. Great. Update, I equal to 2. Still less than 5, so we'll run the block again. Okay, I equals 3. Still less than 5, it's going to run. I equal 4. Still less than 5, it's going to run. I equal 5, it's not less than 5. It's going to be false. It'll skip the block. It won't execute, and it'll continue from the end of the for loop. Okay, so how many times is that? 5 times. 1, 0. 1, 1, 2, 3, 4, 5. 5 times. Okay, there is our for loop. While loops. A while loop is used to execute a block of code repeatedly as long as a condition is true. The syntax for a while loop is while condition block. This checks condition before each iteration. If condition is true, the block is executed. The process repeats until condition is false. So this one just goes from condition to block, and then from block to condition. That's the loop. Here is an example of a while loop. Int I equals 0. We initialize I to 0. While I less than 5, I plus plus, semicolon, it's a statement. Again, I plus plus is shorthand for I equals I plus 1. And this is going to evaluate. So the first time through, I is equal to 0, less than 5, iterate it. 1, less than 5, iterate it. 2, 3, 4. Okay, so 4 passes, okay, and it gets iterated. So the question I'm asking is, what is the value of I after the loop? So when I is 4, this will execute. When I is 5, it won't execute. So 4 plus plus is going to return 5, right? So 5 is going to be what I will be after the loop. I after loop. Okay. So that is our while loop. Very similar to a for loop. And in fact, you don't need for loops. You can always use a while loop if you want, using an iterator explicitly, but a for loop makes it a little bit more syntactically convenient. So there's the while loop. Arrays. The last elementary C object we will discuss is the array. An array is a collection of elements of the same type stored in contiguous memory locations. Each element in an array is accessed by an index called a subscript. The syntax for declaring an array is you give the type of the objects in the array, so the type of the elements in the array, give it a name, the array a name, and then you declare what its size is. So number of elements that are in the array. So here's an example of an array declaration and initialization. Int A, so this is going to be an array of integer elements with 5 total elements, and here are their values. We use braces to do an array literal. So their values, so the value of each element of A is given in this list: 6, 4, -10, 0, and 3. Okay, they're all integers, so we're good to go. To access an element in an array, use the array name followed by the subscript in square brackets. So if you want to get element 2, you have to do A of 2, semicolon. This is going to give us x equals -10. And you might say, no, here is 1, here is 2, it should be 4. No, my friend, the first element in an array has index 0 in C. Second element has index 1. So we say that the C programming language is 0 indexed, meaning that the index of the first element of an array is 0, then 1, then 2. So to get the first element, you have to call the 0th index. To get the last element, you have to call whatever the size is of 5 minus 1 would be the 4 index. Okay, these are the indices. Technically, they're called subscripts in C, although everyone calls them indices. All right, that's arrays. Okay, we're to our example now. We're doing it. Okay, primes in an array. Let's design a program to identify prime numbers that appear in an array A. Consider the following program requirements. The program should define an array A of positive integers. It should test each integer of A to determine if it is a prime. The program should define an array AP of the primes from A. It should print each prime from A, specifying its place out of all the primes found. Taking a high-level approach to designing the program, we can identify two main tasks here. Test if A is a prime. That's the first task. Second task is iterate through an array A and store the primes in the array AP. So let's start writing a function to test if a number is a prime. So we're going to work on the first of these main tasks. Start. All right. So there are several performant prime testing algorithms. Performant means that it's efficient. But we will settle for a simple algorithm based on the ancient sieve of Eratosthenes, I believe is how you pronounce it. There's a paper that Mullen wrote in 2002 on it. It's pretty interesting. So this is the simple determining if the argument of the function x is prime function, C function. So we'll declare I to be an integer. We're going to find the maximum possible divisor. So we'll take the square root of x and we'll take the floor of it. SQRT is the square root. Comes from the math standard library header file, the square root function. The floor function, it will round down. So if we have some floating point number, say this is 2, 1. If you have some floating point number that's between 2 and 3, it's going to round down to 2. If it's between 1 and 2, it's going to round down to 1. And it always rounds down, so even if you have negative numbers, so 0, -1, -2. So if you have like -1.5, it's going to round down to -2. So it always rounds down. Floor. Okay. Good. So we take the floor of the square root, which gives us, this is the maximum possible number that could be a divisor for whatever x is. Okay. So that's what we start with, this max divisor. We compute it. If x is less than 2, return 0. So 0 and 1 aren't prime, right? So we're not going to consider those. If x is divisible by 2, we're going to return 0. Okay? Evens aren't prime. So this x modulo 2 is how we read this. This is the modulo operator, percent symbol. The modulo x modulo y, or mod is also another way of saying it, x mod y, returns the remainder of x divided by y. So we divide x by y, and we give the remainder. So if x is divisible by 2, the remainder will be 0, right? So this will test to see if x is even. No even numbers are prime, so we eliminate those from our possibility. Then all we do is we say, oh, okay, we're going to start at our lowest odd number, and we're going to just try dividing x by that number. And if the mod function returns 0, there's no remainder. That means it's divisible, right? We're going to return 0, which means that we have a number that's not prime. And we're going to continue. So this for loop, the update is going to add 2 to I. So start off at 3, then it's going to try 5, it's going to try 7, all the way up to the max divisor. and it's going to see if any of these divides evenly into x. If not, we're going to continue after the for loop to return 1, which is to say the number is prime. Okay, so that's our little primality function. Now that we have a function to test for primality, we can write the main function to iterate through the array A and store the primes in the array AP. Let's begin with a simple main that tests a single number for primality. So this is a simple main function. It doesn't define an array or anything like that, but it just defines x, and it just says, here's our primality function. We're going to pass it this value of x, and we're going to see if it's prime or not. So px is going to come back as 1. So 1 in C is Boolean true. Boolean means it has 2 logic values, true or false. So in C, 1 represents true, 0 represents false. So if 1, meaning if true, it's going to print the number x is prime, and if it's false, so not true, 0 is the return value, px, then x equals 7 is not a prime. Of course, we know 7 is prime. So we can use this to test the primality function. We could try it with x equals 7. We could try it with different values of x without having to worry about filling out, going through an array and all that stuff. This is an example of a common practice in programming, which is to build something intermediate that works before you iterate on it and make something more complicated. And I say this at the beginning of every class that involves programming, but I still see students every time try to write the program from scratch on the first go. And let me tell you, you're going to save so much time if you just write something that works, even if it's not quite what you want, and then iterate on that. It's going to be so much easier to know where you go wrong. We could use this to debug our primality function. Okay, so to iterate through the array A and store the primes in the array AP, we need to define the arrays and write a loop. Here's a complete main function. So here we actually define an array which includes some numbers that are prime, some numbers that are not prime. Okay, and we initialize a prime array. We initialize it to be 10 large, which is to say as big as A, just because we don't know for sure beforehand if it's going to be, if every one of them is going to be prime or not. So we'll just initialize it to be the same size as A, and then we'll go from there. So here's our for loop. We're going to go through each of these values in the array, and we're going to test for primality. So if primality, we're going to include that prime number in our AP, our prime array, and then we're going to iterate. So once we've collected all of those prime numbers in the AP array, we're going to loop through that and print this prime. So prime, say 1 of 5, 2 of 5, 3 of 5, etc., is given by this array value. So that's the logic. Let's try it out. Okay, so I've got another project here that I'll clean the project so I can build the project. I just put in our functions here. I had to bring in the math header file, but I just used our same code. So now I can run as a local application, and it prints out prime 1 of 4 is 11, prime 2 of 4 is 1901, Prime 304 is 7919, and prime 404 is 2027. So it tested all of these and it selected out those 4, which are the 4 prime numbers from the array. So that's our example, and this last slide just has the references. So, all right, good work. I'll see you next time.